But I will make a few comments now. Oh, yes, I do have one, which actually this is possible that it's yours. I have an exam here that has no name on it, and the cover sheets were stapled on backwards. And I remember having a conversation with someone on Thursday at the end of the examination, where he or she, most likely he, said that he or she, most likely he, was looking for the cover sheet and couldn't find it, and I pointed out that it was the other side of this sheet, and he or she went, oh, duh. Was it you?
That's not my hand.
That's not you, okay. So it's probably Johnny, since he's I am missing, don't have in my possession, Jesse's, Nick Larson, I have a suspicion about that, Mike Luker, I have a suspicion about that, Ryan's, and Johnny's. And since I know this isn't yours, Ryan, and we now know it's not yours, and I believe it's neither Nick's nor Michael's, that boils down to Johnny, yes.
Might be able to see the handwriting real quick? Just so no John's handwriting. Yeah, that's definitely Johnny.
What did you say, by the way?
What?
I have to read your lips.
That was definitely Johnny, yeah. That
It
was-
is his.
I'm pretty sure.
Yeah, okay.
He hasn't, just like new handwriting.
All right. So, problem B1.
Oh, Dr. Sanz,
Yes,
are you going to curve this exam at all, or have you decided yet?
I am not going to curve this examination. Well, I'm not going to curve. I'm not going to curve the average on this examination. Let me put it that way. I don't know if I have previously promised, but I will promise that anyone who's making a serious effort in this course, even if their grade is below what would nominally be passing, will still pass the course because I will curve it in such a way that someone who's trying is going to pass. They might not pass in a happy way, but they will pass, okay? So there is, a percents curve put on everything. The first exam is going to actually have a curve of the average and some squishing of the distribution. Actually, squishing of I won't squish it this way. I'll squish it. I crush it this way. Right. Squish it up from the bottom. But I haven't completely settled on that yet because I wanted to look at the distribution from this exam before I made any adjustments to the first examination. I have a distribution, but I'm not telling you what it is until I feel like it. Okay. I do want to say a couple of things about approaches to the various problems. B1 was the torus. You had that for home. And some of you still didn't get it right. The way that you want to think about that is that you've got a circularly symmetric distribution. And let's say, so the current is going up on the outside and like so. So the actual real currents in this circuit, so this thing goes, right, are flowing this way. And it is to your advantage to use Ampere's law in the integral. Which I won't do for you here. Then you need to use linear relationship that I think I gave you on the problem. I said that it's mu, the relationship, permeability of speeds. So from in the first part, Ampere's law, you can find B and H because the permeability of what's inside the toroid is 1. The second part, what you have to remember is that the thing that you can calculate easily is H, because that's only responding to the real currents in the problem, and you know what the real currents are, right? Then you can calculate B from that. But you don't start with B and then calculate H as being B over mu, right? Because the currents that you know are the real currents. Now, what's going to actually end up getting generated here? I'll let you do the arithmetic, but basically the form of the magnetization in this in the middle is such that it just enhances the H field that was there to make the B field. Right? It's a linear enhancement. And so the actual form in here is just as though I had this current, except that the current is increased a little bit by the surface currents that you get from the magnetization. In fact, their currents are increased by a factor of mu. So the bound currents are parallel to the real currents and are some factor. They're not larger. You can work through the relationships between B, mu, H, and M in order to figure out what the bound currents actually are, right? You should go through and do the work to demonstrate to yourselves that the bulk bound current is 0. Any questions? If you do, shout.
What's the symbol that denotes the bulk bound current in this case?
I think we've been writing it like this. J sub B. And the other one was K sub B. So those are the surface currents, bound currents, and the bulk bound currents.
But that's not K sub M and J sub M.
K sub M and J sub M work.
K sub M and J sub M are related. Actually,
They're the same. It's the same
they're the
notation.
same thing.
It's just
Okay.
the different notation. I write it on something.
But a mistake that a lot of you made was saying, oh, I got the B field already, and then given B, let me calculate H from that same current. And B is the result of the bound and free currents. So you can't plug that current back in again to get B. All right, problem 2. This was turned into a solenoid. And once again, integral forms serve you well. That is that the electromotive force, integral of the field around closed loop, is equal to and I just dropped a factor of 4 pi over c, I think.
Just 1 over C.
1 over c.
So your notes still missed the negative sign on mine.
Yes.
Lens is long.
Minus sign amongst crayons.
I mean, brings you closer to Faraday.
That's what it is.
Okay, given that, now you need the flux. Flux. This is the actually I'll just write it like this. Magnetic field for solenoid, which you can solve for using Ampere's law if you like. You definitely don't want to use Biot-Savart for it. And you definitely don't want, well, you could solve for the vector potential, but you really don't want to do that either. You can solve for B in the solenoid, cross-sectional area, and that's it, all right? In terms, you solve for B in terms of the current. The inductance, a lot of people didn't get the first part right, but they could proceed and just find the second part, which was the inductance, which was the magnetic flux divided by the current. I won't tell you what that is, you can work it out. And then you had a choice, actually, the EMF from end to end, all right? Every time you go around the loop, you have one of those EMFs, EMFs. And so you go around at n time, you have n times that EMF. Or you could use E equals minus L mod T. Yeah.
Are you listing constants though, out of curiosity?
Oh, you mean C's and stuff like that?
There's like
There's
a number of
C on-
turn, isn't there a number of turns?
Oh, okay, it depends upon how you want to
Define.
Oh,
define
okay.
that.
Alright.
I actually
There should be one
randomly
over
switch between defining that as the flux through one loop and the flux linkage
Okay.
through n
Then
loops.
there's also C in the bottom.
This is more intended as a pointer rather than a solution, what I'm doing right now. Because some of you should, well, all of you, some of you could just copy what you wrote on your exam back down again. And some of you need to work your way through it. That was it, right? Yeah. B3. How many of you are TAing for Physics 2? How many of you noticed that this problem was on the last Physics 2 exam? It was.
I thought we had this very hard.
On the second exam or the
The
first?
second examation in Physics 2.
No, who knows, I noticed the T.
And this is why you didn't want us to come.
Yeah.
Oh,
Studying
I
for
forgot.
this.
But he knew, oh, he knew. Yeah.
It wasn't the same question though. You did it over.
No, it wasn't the identical same question. I asked you to do a little bit more arithmetic.
They had the whole charging section.
Yeah.
So it was 0.
Yeah, okay, so,
That was my.
it's a capacitor. Charge on the capacitor is equal to, be sloppy about it, right? The, what do I mean? The electric field across the capacitor is equal to 4 pi sigma 4 pi q over the area. All right, that, because that's a function of time. All right? And the magnetic field can be found from some set of constants. This is for Ryan. Okay? So you can, the magnetic field depends upon the distance from the center of this, this capacitor. Grows linearly to the outside. And then drops this one over. Then you're asked for the power. You have a variety of ways that you can solve that. One is that you can just find out how much energy is stored in the capacitor in the first quarter cycle as it charges. Well, yeah, the current is right as it charges. So yeah, you can find out how much energy is stored, or that's probably the easiest way. And so you need capacitance, that's where T comes in. What do I want to say about this?
You take a
Not much.
derivative?
What?
You take a time derivative, because you want power, or?
Yeah, you want power, no.
Nope.
The average power in the first cycle.
That would be here.
Yeah, that's it. We're trying the total energy stored divided by the time, the quarter cycle time. Right, and then the last part is, aside from multiplicative constants.
Big T.
I'm writing it this way because the textbook writes it as H, and that's fine for linear materials, but for most other situations, well, H would have worked fine here, no problem, because B was 1. You're safer using B. I think I even know what the constant is.
For C over 4 pi,
Over 4 pi?
because it's over mu naught.
Okay, then I'm going to erase this. Leave it at that. That was B3. B4. Most of you got full credit for that one. Some of you did much more work than you needed to do. There is no magnetic field in the frame of the charged sheet. It's not moving, no field. If you have a field, then the calculation gets really hard. If the field is just an electric field, then the calculation is easy. Okay. So that's all my comments on the examination. Any questions? I'm trying to think about the multiple choices. 2 of those multiple choices were from recent Physics 2 for the Masses examinations. 3 and 4.
One was also,
1 was also on a recent Physics 2 exam.
so that's 1, 3, and 4.
So that, yes, that's correct. Problem A2 has not been on any recent Physics 2 exam, to my knowledge. Okay,
First, we needed to see some percentages.
now for something completely different. Okay, so if you want me to take another look at something, just put a note on the front, give me the examination back. If you think that I need to be completely informed on just what you were thinking, then hold off on making the argument to me until I can hear it again. I'll do you much better.
So what is that, like next week?
I don't know.
Okay.
Usually it's about 3 or 4 days. It's been 3 days now. So I spent a very quiet weekend. It's nice. Well, half quiet. This side I'm still okay with.
So I'll just check that.
Did you?
Oh, yeah, you might want to, like, de-germ your hands before you eat after touching these exams.
Okay.
And I would suggest that you perhaps want to autoclave them, you know. Just stick them in an oven for a while. Over 140 degrees ought to do it.
Makes them look nice and old-timey if you don't leave them in. too
Does it
long.
brown the paper? I don't know.
If you leave them
140
in-
doesn't brown
Why
the
would I
paper.
want this?
Not if you use soap and water.
What was I going to talk about today? Pointing vector, talked about that. All right,
A little bit, not much.
yeah. Good enough for me.
Where's the closest autoclave oven?
What?
Where's the closest autoclave oven?
Probably in your dorms. It's called an oven.
Wait, can I put paper in my oven?
At a low temperature, yeah, 140 degrees.
Paper doesn't burn until 212.
You live in Polly, don't do it.
Fahrenheit 451 is the temperature.
Well, actually, no, he got that one wrong.
No, I'm joking, Jeff.
Well, that's what I'm going to stick with because that's what I learned.
Yeah, probably.
No, 212 is boiling. I'm an idiot.
Or somebody.
In an oven outside.
You're going to tell me that he made up things about Mars?
I mean, I believe all of it. We're living with aliens right now. I don't know, I don't have any of it. I've read most of it though.
By the way, the exam grade distribution actually looked like this. Okay. You guys will still pass, but I'm unhappy. Actually, that's a lie. Maybe more like that. If you're in here, talk with me. Bring money.
I thought it was credit card numbers.
Credit cards are tracing.
Ah.
All right. So, I'm actually going to give you, I may have done this before, but I'm going to do it again now anyway. A little piece of a Physics 2 lecture, because I like it. That's what I want you to consider. I heard that. That's good.
Progress has been made.
Yeah. I want you to consider what happens if I have got my axis here. What I'm going to do is, along this line and the region around it, I'm going to have a magnetic field that points out of the board. So if you were looking at edge on, there'd be some region there. Where the field is pointing out of the board at you. Okay? And I can create that field by having a solenoid there, for example, and then just oscillating the current through the solenoid. Because what I want to do now is I want to change the field as a function of time. But it's just pointing, it's just here, and now it's changing as a function of time. Let's say it's increasing in this direction. Right? And what do we know about that? We know that there's going to be an electric field. Since I'm taking this out of my Physics 2 notes, I will be very blatant. That's just awful. Is it very squeaky?
Yeah, tell me
Yes.
you're recovering your hearing.
It's like normally I don't hear it that well, but today I'm hearing it. I believe that when I have the chalk, I just take the frequency up so that you can't hear it. But we need a good microphone to figure out whether that's true.
That can be arranged.
So, I've got some region here. There's a little dx here. Let me put this is the height of the region over which I've got my field. And aside from a constant, I can write that the integral of the electric field around that loop is going to be the rate of change of the magnetic flux through the loop. So I make a magnetic field which changes in time. And I end up with an electric field for which there is an integral around the loop. So let's see. This is dx. That means that I've chosen that to be my x-axis. and that to be my y-axis, right? That my electric field, taken around the loop, if I make this sufficiently small, I'll make this small enough that I don't have to worry about the ends when I do my integral. They're gonna be small compared to everything else. Then I've got EYH plus, let's say, Y at position X. This point here is X plus dx, let's say. EY of X plus dx H plus the ends that I'm going to ignore. And then, because I'm taking my integral this way and that way, I'll do it that way. Doesn't matter which way I go around. I've just chosen to go around in such a direction that this is positive and that is negative. But this is negative and that is positive. And yeah, okay. And then I could write EY of X plus dx as EY of X plus EY dx. Right? I just did Taylor expansion. Right? So this ends up being EY dx H dx. No. That. And that's equal to the rate of change of the flux, which, if I wanted to write it out, yeah, I will, is H dx dV dt. H dx goes out of both sides. I know I probably dropped a minus sign there. And I end up with dEy dx equals minus dV dt. That is, a time-varying magnetic field gives rise to a spatially varying electric field. If I write out all of the terms, then I actually end up with, oops. This was xy, this must be z. I want to make sure that I keep the proper term there. This is the magnetic field that's pointing in the z direction, perpendicular to the loop that I just chose.
So you're gonna change it in the upper equation too?
Okay, I'm happy now. Okay. I can do exactly the same thing by taking an electric field, constant electric field that makes a plane wave, let's say. And the electric field is varying with time. And I can end up relating the time variation of the electric field to the spatial variation of the magnetic field, spatial gradient of the magnetic field. In MKS units, there ends up coming out a constant there that I'm about to buzz through, and I'll include the constant, because it will end up being equal to the speed of light. So it's really easy to show using the integral